Good morning, everyone. In this session, we are going to discuss about the different types of regression. We already discussed about simple linear regression, multiple linear regression. There is another type of regression, that is polynomial regression. So what do you mean by this polynomial regression? So when we see this simple linear regression, we can easily say that it is going to give us a straight line, okay, which describes the how best it is fitting the model. And the equation to solve this is y equal to b naught plus b1 into x. And also we can also say that y equal to mx plus c. It is a simple straight line equation. That is what the simple linear regression. And coming to the polynomial regression, as the diagram itself indicates, it's not linear. It is non-linear data. If it is linear, definitely we are going to get a straight line. When the data is not linear, we'll get something like a curve. So this representation indicates that it is a polynomial model. And the equation to solve this regression of polynomial is y equal to b naught plus b1 into x plus b2 into x1 square, and so on. So what is the difference between this simple linear regression and the polynomial linear regression? So if the relationship between the independent variable and dependent variable is linear, then we can use a straight line to fit the given data. That is what this simple linear regression. So this is line of regression. These are the data points, and we have a independent variable and we also have a dependent variable. But coming to the polynomial regression, if the relationship between the independent and dependent variable is not linear, okay, then when we are going to implement such nonlinear data with the help of a simple linear regression, it will result in large errors. That is what the disadvantage with this is simple linear regression. So to work with nonlinear, there is some situations can occur where we have to work with nonlinear data. At that time, we can't use this simple linear regression or multiple linear regression. Then we have to go for another regression that is called as the polynomial regression. So the problem of this linear regression can be solved by two methods. One is just simple transformation of nonlinear data to linear data so that the linear regression can handle the data. That is one way how we are going to overcome the problem of nonlinear nonlinear data. And another one is we can implement directly with the help of a polynomial regression. So what is this polynomial regression? This is a type of regression analysis that models the relationship between independent variable to the dependent variable as an nth degree polynomial. Not between independent and dependent, but between the independent variable to the dependent variable as an nth degree polynomial. And this polynomial regression is used to model a wide range of relationship between independent variable and dependent variable. That is, if the linear relationship is curvilinear or quadratic or cubic. If any of this relationship is there, then only the solution to model is using the polynomial regression. So, the degree of the polynomial equation depends upon the complexity of the relationship between independent variable and the dependent variable. A higher degree polynomial, if you are taking a high degree polynomial, yes, of course, it will better fit the data, but sometimes it also overfit the data that results in the poor performance on new data. Okay. So polynomial regression can be performed using the same techniques like linear regression. That is, the coefficients of this polynomial equation can be used using the least square methods. In the last class, what we discussed, how using least square methods, how we have find out the coefficient for simple linear regression. In the same way, we can also find out the for polynomial regression also. Why we are going to use is that which minimizes the sum of the squared errors between the predicted values and actual values. So when we discuss about this polynomial equation, it will represent something like this. You can see. So in this 2 is the exponent and x and y are the variables. This 5 and 2 are the coefficient and this is the constant, and these plus and minus we can say it is a operator. This is how the polynomial equation will be. And coming to this equation for polynomial regression is, it is represented as y equal to b naught plus b1 into x, b2 into x square, b3 into x cube, so on, up to bn to the x power n. And the polynomial regression curve will be something like this. You can see it is not like a straight line equation. It is something like a curvilinear. That's why we call it as a polynomial regression. And where we know that y is dependent variable and x is the independent variable, and these b0, b1, b2, bn are the coefficients. Okay. And the degree of the polynomial equation n determines the complexity of the relationship between the independent variable and the dependent variable, this n. To what nth degree polynomial will use, that it is going to give you the complexity of relationship between the independent variable and the dependent variable. And when we see the types of regressions, we know that it is three types: simple, multiple linear, and polynomial. Simple linear regression is given by this equation, we know already. And multiple linear regression is something where we have more than one independent variable. That's it. The only difference is here we'll have one independent variables. Here we're going to have more than one independent variable. That is the difference between simple linear and multiple linear regression. And the polynomial is, it is represented as b1 into x1 plus b2 x1 square, so on up to b2 bn x1 to the power n. So these are the three different representations. And when we differentiate linear regression, that is simple or multiple, and this polynomial, it assumes a linear relationship between dependent and independent variable. And the model is expressed something like this, where we know what is y, what is b0, what is b1, intercept and slope. And it is easy to interpret and can make predictions within the range of the training data, but it doesn't suit with the nonlinear relationships. Okay. And whereas coming to this polynomial regression, it extends linear regression by adding higher order polynomial terms to the model to capture the nonlinear relationships. And it is expressed something like this, where this k, or you can also say it is n, is the degree of the polynomial, and it provides more accurate predictions for nonlinear data sets, and it is more flexible in capturing complex patterns. But however, there is some disadvantage that complexity is more to implement, and sometimes chances of overfitting the data if the degree of the polynomial is too high. So these are the differences between normal linear regression and the polynomial regression. Okay. Now, the end of this linear regression, that is the metrics. In the last class, when we have implemented this linear regression, I told you we are to evaluate a model, we are going to use R square. But it is a statistical measure R square. It is going to show you how much variation is there between the independent variable and the dependent variable. If you and it always ranges between 0 and 1. If you get more than 90%, then we can say that our model is the best fit model. With the help of R square, we are going to find out the statistical measure of this linear regression. In the same way, at the same time, we have to calculate sum of the errors. How much least sum of squares we will get as errors, then we can also conclude that ours is the best fit model. For that, this linear regression metrics, these are the 5 metrics we are going to use. One is mean absolute error, mean square error, root mean square error, relative mean square error, and the coefficient of variation. Let us derive with one example how we are going to calculate all these types of errors. Okay, let us use one solid example and we'll find out all these errors. Now here consider there is a training data, there is a test data, and we have some 2 fresh items whose actual values are 80 and 75, and our model predicted this as 75 and 85. Okay, this is actual value, and our model predicted these values. Now let us find out these metrics or errors for this particular given model. The very first one is the mean absolute error. Mean absolute error is given by 1 minus n I equal to 0 to n minus 1 yi minus yi gap. This is nothing but the absolute values. So this yi is the actual values, y cap is the predicted values. So 1 by n, how many test items we have? 2. So 1 by 2 into 80 minus 75, actual minus predicted, actual minus predicted. Here we'll get minus 10, but as we are taking absolute values, so negative signs will be discarded. So total we are going to get it as 7.5 as the mean absolute error for this particular given test data. Okay, so this is the formula for calculating mean absolute error. Similarly, next one is mean squared error. So it is given as a name itself indicates square. So it is same like earlier one, but the only thing is it is square, not the absolute values. Just directly we are going to square these errors. The same thing over here, but here we are going to square the values and no need to take any absolute. Well, even though if you get the negative values, when we are doing square, now it will become positive, and the total mean square error is 62.5. Of course, we got more. So to overcome this, we are going to use next one, root mean square error. So the root mean square error is nothing but the square of the mean square error. So the square root of 62.5, we are going to get 7.91, which is very less compared to this mean square error. Okay. Next one is relative mean square error. So it is given by yi minus y cap whole square, that is actual minus predicted. Here yi minus y bar whole square. So how we are going to calculate yi? Now we know y predicted value we know, actual value we know, but we have to find out the y mean. So for finding this relative mean square error and coefficient of variation, the training table should be used. This training table should be used to find the average of this y. So let us calculate the average of y, that is 80 plus 90 plus 100, so on. So it is 500 divided by 5. We got it as 100. Now, relative mean square error, just place the values, that is yi minus y square. So you can see that 80 minus 75, 75 minus 85 already we done. Here 80 minus 100, 75 minus 100. So we got very less, that is 0.1215. Okay. Similarly, how we are going to find out this coefficient of variation is, it is nothing but the relative mean square error divided by y bar. That is this one, relative mean square error divided by y bar. We know that we got it as y bar has how much? 100. Okay. So relative mean square error is square root, relative mean square error is, okay. So this, it is giving it as 0.3. Okay. Sorry, this is not relative mean square error, root mean square error. Okay, so coefficient of variation is given by root mean square divided by y bar. So we got it as 0.08, that is very less. So that it indicates that ours is the best fit model. So when we are evaluating a linear regression model, remember, first we have to find out the R square. Okay, how much you get, how much more you will get if it is above 90, above 9, then ours is the best fit model. In that way, we can conclude about linear regression. Another way is we have to use this linear regression matrix and we have to calculate all these errors and how much least of these errors will get, that much accurate and that much best fit model we have implemented. Thank you.